Hello, everyone. I am Jianing Han from Professor Sijin Li's lab. Today, I will introduce my poster. The title of my poster is Complete Biosynthesis of Berberine in Saccharomyces cerevisiae. First, I'd like to introduce the background of this project. Berberine is a kind of benzoisoquinoline alkaloid. Benzoisoquinoline alkaloid is a diverse group of plant secondary metabolites. It has a lot of medical properties, especially berberine, the active compound of traditional Chinese medicine named Huanglian. As this kind of plant is a widely used antimicrobial. It also exhibits some anti-cancer and anti-diabetes potential. Now, that's very helpful for human. However, the supply chain based on the agriculture, the farming of plants, could be very costly and also require the suitable climate, and also that is very susceptible. So this fragile agriculture-based supply chain is not very suitable to meet the requirement of commercially production of berberine. And now the development of synthetic biology makes it feasible to produce BIAs such like berberine in some heterologous hosts, especially in some microorganisms. That in fermentation, microorganisms can grow very fast and the cost is very low. Especially Saccharomyces cerevisiae, also known as baker's yeast, is more rapid, cost-effective, efficient, and environmentally friendly. The project is to reconstruct the berberine synthesis pathway in yeast. So first, we need to have a brief knowledge about the berberine synthetic pathway in plant. Briefly, it can be divided into three parts, starting from tyrosine, a simple endogenous amino acid. The first part is formation of nocochlorine. This compound is the first compound with a benzoisoquinoline alkaloid backbone. After that, the second part contains several modifications to the backbone, such as methylation, O-methylation and N-methylation. And that will form reticulin. That is an important intermediate in this pathway. And the final part is berberine production. Based on that, I constructed the berberine synthetic pathway in yeast. The module one is the formation of the berberine from tyrosine to nocochlorine. I introduced three enzymes to this part. And secondly, I introduced 4 enzymes for the second module. That's for the BIA backbone modification from nocochlorine to reticulin. As a proof of these 2 modules, I test the yeast by LC-MS. For the first module, I got a clear peak in my string named berberine 1. I can see a clear peak of nocochlorine in this string in the LC-MS. And after I introduce the second module to yeast, constructing berberine 2 string, I can also see a clear peak of reticulin in the berberine 2 string. And finally, I introduce the third module to these strings and with 4 enzymes. And that catalyze the reactions from reticulin to berberine. I also tested the compounds by LC-MS. I found that berberine was successfully produced by this string, but the titer is not that high, about only 2.23 microgram per liter. And the upstream compound, cannadine, the production is about 162.5 microgram per liter in the third string. So that indicates that this step may be a bottleneck for the berberine production. And in the future work, I may need to do some optimization for this step. And as a conclusion, I constructed the berberine synthetic pathway in yeast by introducing 11 heterologous enzymes, 3 modules, divided into 3 modules, and achieved the complete biosynthesis of berberine yeast. Next step is to further optimize this pathway and increase the titer by increase the efficiency of the rate-limited reactions, such as the final step. We also want to further expand the pathway to other valuable BIA products and derivatives. Thank you very much.